All right, folks, welcome. Hopefully, online folks can see and hear me okay. Um, it looks like we have a bit of a smaller crowd today, and I would say that's maybe partly, I think COVID is making the rounds again, and we got great spacing in this room. So, way more than 6 feet if you want. You can each have your own section if you want here. I hope everyone home is feeling okay. And yeah, good to stay safe, I guess, if you can. I guess it shouldn't be a surprise, like with masks coming off, now all of a sudden we're going to probably get a big wave. But anyway, that's life. So today we're going to continue our topic, which was on water, drinking water, kind of in particular, we were talking about. And we will be starting on second topic today. The drinking water one should go by pretty quick, I think. Second one is on cannabis. And so what that means is the due date has now been set for the water unit assignment, and it'll be 7 days from today, so it'll be next Tuesday. And I think in the past, I may have had some like confusion regarding the exact due time. I think some of them were due at like 1 p.m. and some were due like at midnight. I'm setting it so all future ones will be due like a minute before midnight, which is the last minute of the day I can set it for. So that will be due a week from today. There are the other one, the previous one, global warming, is due today. So if you haven't finished global warming, now would be a time to go in and check to make sure that you have done it. And a new one opens today, which is on the cannabis unit that we will hopefully get to in just a little bit. Other than that, we're rolling along pretty good. Depending on how time goes, we may finish all our units, which would be better than I guess we expected. And I don't feel like we're rushing either. I feel like we're doing well, we're taking our time, and things are just moving along well. Cool. Everyone's happy, it seems. All right, so we have been talking about water. We talked about all the various methods to purify water. Talked about how when you're purifying water, typically there's sort of two parts of it. One is you want to remove any chemical substances from the water that might be harmful or unpleasant. And you also want to remove any like biological things. And for the biological things, really, you just want to kill them. Necessarily, removing them isn't always going to be necessary. And so we looked at things that kills the organisms, which is what we call sanitation. We looked at using chlorine. We looked at, what is it, like ozone, UV light, heat. There's a whole bunch of different methods you can use to kill the microorganisms. We looked at the pros and cons. We also looked at methods to remove things from water, like charcoal filtration, ion exchange, reverse osmosis, a whole bunch of different methods. And so it's nice that we have not just one method, but many methods to make sure that we have we have adequate access to clean water. The last little sort of, subunit, I guess we'll say that I want to talk about is the issue of drinking bottled water versus tap water. And this is an issue which has much less to do with the safety of the water you're drinking and more with sort of associated environmental and social issues that are kind of attached to this. This, by the way, is a picture of former Acadia students. This is probably 10 years old now. There was actually a group on campus, like a ASU student club, that was devoted to improving access on campus to clean drinking water. And as a result, reduce or eliminate our reliance on bottled water sources. And I think this kind of came out around the time the biology building opened. And at that time, the new building, brand new construction, $50 million building, there were no drinking fountains in the whole building. And so those have since been installed. So with the access to clean drinking water is actually much better here than it would have been even, say, 10 years ago. Due in part to student activism. US bottled water consumption per year in gallons per person per year. This only goes to 2012, but you can see the trend. The number is around 30 gallons per year. When you think about a gallon is like 4 liters, which is about 8 bottles of water. So 8 times 30, what is 240 bottles? So that means the average American drinks about 240 water bottles a year, which is, 2 every 3 days or so, which is a lot of bottles. And obviously that number has been rising dramatically since the early 1970s. And actually I'm old enough to remember being a kid, and I grew up in Antigonish. Close to my house was a corner store, and I'd go there. We used to actually right next door to the corner store was like a bottle exchange place. So when we were kids, we would go hunting for bottles wherever we could and trade them in for 80 cents or whatever we could get for it, and then just go next door and blow it on junk. And my favorite was Lime Crush, which is really hard to find now. But if you can find Lime Crush, buy yourself a can. It's good. Anyway, I remember buying it one time as a small kid. I was probably, 8 or so. And I looked in there and I saw bottles of water for sale. And it just floored me as a kid. Who would buy water? There's pop right here, and you're going to pay the same price and just get water. There's an infinity water at my house for free. Of course, I grew up and realized there's lots of opportunities, lots of situations where you may prefer water over really any other drink. But there's no doubt that our reliance as a society on convenient bottled water is definitely, it's a new invention, really. It's the last 30 years, really, 20 years that has really gotten big. So where does this bottled water come from? This might look familiar. Dasani, which is Coke product. There's each of the big, companies, like Pepsi, I think, has Aquafina. They all have their own brand. And Dasani, it says right on the bottle, to create Dasani, Coca-Cola bottlers start with the local water supply, this tap water, then filtered for purity using a state-of-the-art process called reverse osmosis. We know what that does. We know it removes anything dissolved in the water. Then the purified water is then enhanced with a special blend of minerals for a pure, crisp, fresh taste. So essentially they take tap water, remove all the minerals, and then add the minerals back in a specific proprietary ratio. And it's mainly done for taste, that, slight variations in how much carbonate or how much sodium or whatever can have some impact on the freshness of the water, how it tastes. The biggest issue, I'd say, around bottled water, or maybe one of the biggest issues, is the garbage problem that's associated with the bottle itself. The bottles are made out of plastic, and we're going to be looking at plastic in a future unit. 2017, 50 billion bottles of water were purchased in the US, and only about 10% were recycled, meaning 90% of these went into landfills, or even worse, into the environment. So that is a gigantic issue for something that is arguably unnecessary, entirely unnecessary for most people in most situations. There are situations where, I agree, bottled water is maybe a must. So for example, if you are going camping in the woods for a week, you may want to bring a jug or two of bottled water, and there's no municipal water supplies in places like that. But I guess you could use reusable jugs there too. This is an ad campaign basically trying to make the argument that drinking bottled water is essentially like you're drinking oil. And not from a health perspective, but just from the idea that oil is what is used to make the bottles themselves in the first place, the plastic. So you're consuming plastic, not ingesting it, but consuming it in a way that you are using it and causing it to be created in the first place. And then all the associated issues around that as well. Now it's interesting to note that this ad campaign, see filterforgood.com, this was actually produced by Brita Water Filters. So Brita Water Filters was trying to, cast consternation on the practice of using bottled water, trying to get people to buy more of their filters because, of course, if you filter your water with a Brita filter, you shouldn't need a bottle. So fountain, I guess, you know, it's just tap water. There's publicly available. And this is a funny slide because, like, this is now kind of frowned upon with COVID, right? I don't know if it is. Like, I don't know if fountains are actually an important source of COVID transmission. All I know is that all the drinking fountains on campus were, like, blocked off once COVID started. So I think you can use bottle fillers, but you can't, like, put your mouth close to the, I don't know. That'd be an interesting thing. Remains to be seen. I remember around 2000, you know, the awareness of the waste associated with bottled water was really becoming better known, and it became kind of a trend for people to carry water around with them. And using reusable water bottles, and the brand, I don't know if you've ever seen these before. It was funny because it was like in the year 2000, 90% of people walking around campus would have one of these attached to their bag or in their hand. And this is before I was here, of course, but like I was in a university at the time, and everybody had them. They were these Nalgene bottles. I found this kind of funny because I worked in a lab. Oh, do you have one? Yeah. Is it Nalgene? Yeah. Perfect. Exhibit A. We have a Nalgene bottle in the wild here. So these Nalgene bottles these have been used for decades in scientific settings as like storage bottles for different solutions and things like that. But they kind of crossed over into the mainstream market for carrying water. And later that decade, like probably late 2000s, they came under actually quite a bit of scrutiny because they were made from a kind of plastic called polycarbonate. And polycarbonate is a kind of plastic that's used in all kinds of different applications. But it was figured it was ideal for making these bottles because they're tough, it's durable, it doesn't break easily, it doesn't wear down easily, and it had kind of all these properties that people wanted to have in these bottles. You could basically drop the bottle on the ground, kick it around, you didn't have a risk of anything really bad happening to it. So what is this bottle? It's polycarbonate. It's made out of a plastic which uses two different molecules, one called phosgene and one called bisphenol A. And when you mix these together, they form these like super long chains. And this picture that I have here is a segment of a molecule, and you can see it says N. And what this means is this segment is repeated in a line again and again and again. So you get these super long thread-like molecules, and these kind of pack together, weave together to a certain extent, and make up the plastic that makes up the walls of the bottle. Now, one of those ingredients, which is this piece here, which was used to make it in the first place, is made from a molecule called bisphenol A. And bisphenol A, sometimes also called BPA, is the ingredient that's used to make them in the first place. And so when the bottles are made, the bottles can actually contain a very small amount of BPA still kind of unreacted, but in the matrix of the plastic. So this polycarbonate is used for more than just water bottles, used for all sorts of things. This is 2006, and I'd like to see this graph for today. 32% of the polycarbonate made in 2006 was for optical media, which was CDs and DVDs. And I don't know, it's been a long time since I bought a CD or DVD. So I'm wondering if that 32% is like 3% or something now. I feel like these, like if you buy a modern computer, that you can't actually play a CD or DVD, right? So they're almost obsolete, I'd say. Electrical, electronics, blend, construction, medical healthcare, bottles and packaging, et cetera, et cetera. So a lot of this stuff gets produced every year. And this little bit of bisphenol A that could potentially leach out of the plastic into your water has been implicated in some studies to possibly have negative health effects at small doses. And this was an interesting topic when it first came out because some of what the early claims was that it behaves the opposite of what you'd expect compared to Paracelsus's quote, you know, the dose makes the poison. that what they were suggesting was that large doses actually have very small impacts on people, but going to really low doses, the idea was is bisphenol only at low doses can start to trick the body into thinking it's a hormone and can therefore have biological effects that aren't present when it's present in high studies. So all the toxicity studies, they said, don't really matter because they were all at high doses where we don't see effects at high doses, which would be a weird but intriguing thing and worth definitely more study. Okay? So this was what I thought it looked like. Estradiol is the compound on the left, and estradiol is a sex hormone, female sex hormone, and it's in the estrogen family. Like estrogen isn't a single molecule, it's a collection of a variety of molecules. One of those molecules is this one, estradiol. And if you look at the structure here, you can see it's sort of like a bunch of carbons in this framework with an OH here and an OH here. And we know that OH is hydrogen bond. We know that's the sticky part of the molecule. That's the part of the molecule that's likely to interact with receptors in the body and things like that. So bisphenol A, by extension, has a bunch of carbons in the middle with an OH over here and an OH over there. And so they're, just by looking at the structure, it's similar in size and shape to estrogen or estradiol, and therefore it was believed that it could have an estrogen-like property on the body. And what they would call these things were estrogen mimics. And so they, the idea is that you're exposed to bisphenol A, hypothetically, you could start to develop biological traits that were consistent with what you'd expect from high dosages of, or additional supplemental dosages of estradiol. So almost right away, people took the precautionary principle, which is, let's be careful, okay? Let's ease ourselves into this. In 2008, Canada actually became the first country to label bisphenol A as toxic and banned its use in baby bottles. So the idea being, if you're undergoing active development, you're more sensitive to the impacts of hormone mimics or estrogen mimics than you would be if you're a fully grown adult. Sunoco, largest BPA producer in the US, stopped selling it to manufacturers of baby goods. And then in 2009, the National Institute of Health in the United States released $30 million in research grants, basically saying, like, we don't really know enough about the health effects of bisphenol A. For precautionary reasons, we're gonna suggest babies don't come in contact with it. But we need to study this more. And we're gonna put the money where our mouth is and incentivize research groups to look into this particular substance. And so what followed was a lot of work, a lot of papers. One that really, I think, captured the attention of the public was this one, which says, occupational exposure to bisphenol A and the risk of self-reported male sexual dysfunction. And what they did in this paper is they went to China and they went to a factory that produced a lot of bisphenol A for the purposes of making polycarbonate plastic. And they did voluntary surveys with all the workers, and they were able to sort of estimate their lifetime exposure to bisphenol A. And they were asking the questions about their sex life. The idea being that their sex life was in some way related to their sex hormones. And so what they found is that those that were exposed to the most bisphenol A had the highest risk of self-reported sexual dysfunction. So then people sort of immediately made the connection between drinking from these bottles and their sexual performance. And very quickly, those Nalgene bottles went from the most popular thing in the world to, oh, maybe there's something to be worried about here, to these things are the devil. And people basically just en masse chuck them out and replace them with other things. Now, if you have one now, you have nothing to worry about. Actually, the company changed the plastic that they use in these bottles, so it's not the same bottle now that it would have been then. But even if you have a legacy one, I'm going to tell you now that there's nothing to worry about with drinking those either. First of all, in this paper that came out in 2010, I guess originally November 2009, these are people who, because of their work, were exposed to huge doses regularly over large periods of time. That does not mean that the dose you would get from regularly drinking from a polycarbonate bottle has anywhere near the same amount of risk, even though it could be the same chemical substance in both cases. And I'll get to the current thinking on bisphenol A in a few minutes. So the trend switched almost overnight to from the Nalgene bottles, the bisphenol A bottles, to steel, stainless steel, or aluminum. One ironic thing is that a lot of these stainless steel bottles actually had polycarbonate liners on the inside. So the inside was lined with the same sort of plastic as before. So only the outside shell was different, and so there was actually no real difference. Then you'd start to see bottles with this label on it, BPA free. And you might actually see this still. Like you might, when you're buying these bottles, sort of this memory people have of bisphenol A being temporarily the worst thing ever, you'll still see this sort of thing. And this sort of label, I think, will be there and it'll stay and then it'll like fade. Just like with dish soap, for a long time it was phosphate free, big signs on it. And there were like little signs, and now they're hard to find because, people don't, it doesn't incentivize people to buy things like that anymore. So you can get the BPA free ones for sure. So what was the result of all that research that was done? Well, 2015, a paper was published, an opinion paper by the European Food Safety Authority. And they had a panel on food contact materials, enzymes, flavoring, and process aids. I'd like to add, too, that this bisphenol A wasn't just used in Nalgene water bottles. It was also used in cans. So if you buy canned food, the liner inside the can, like I don't know if you ever took a can and opened it with a can opener. It almost looks like there's a plastic film inside. That plastic film provides a barrier between the food and the metal, so it prevents metal from leaching into your food, and it keeps the food fresher longer. That is often bisphenol A as well. And they say this: the panel concluded that there is no health concern for any age group from dietary exposure and low health concern from aggregated exposure. They noted considerable uncertainty in the exposure estimates for non-dietary sources, while the uncertainty around dietary estimates was relatively low. So essentially what they're saying is from your food and drink, you can't be exposed to enough of this for it to cause you any problems. However, your total exposure will depend on what you do with the rest of your life, and maybe there might be health concerns for you in that case. So what they're saying is those people who reported high rates of sexual dysfunction in that factory in China weren't experiencing symptoms because of their diets. They're experiencing symptoms because of their occupational exposures. Okay? But what they're talking about is through food, which is how almost all of us would be exposed to this. Like if you set up a business in your garage melting down CDs or something like that, where you have access, a lot of exposure to this stuff, then your personal risk could be quite different. Health Canada, as of 2020, they have recently done a chemical risk assessment. This is what they found in 2020. Our exposure levels are actually lower for the average human in Canada than they used to think. Most Canadians are exposed to very low levels that do not pose a health risk. BPA in food packaging is not a health risk to Canadians, including newborns and children. So the reports that seem to be most recent and coming in now seem to be that the doses we are exposed to, at least, are not a cause for concern. Cool. The last thing I want to talk about was fads that come and go with drinking water, which are always interesting to see. One of them is alkaline water, where water can be acidic or basic or neutral. When you drink water that's 100% pure and has no dissolved gases, it is neutral and it has a pH of 7. If it's lower than 7, you have acidic water, like what you'd have with acid rain, which can have a pH of like 4 to 5. And your stomach is much more acidic, has a pH of like 3. But if you go above 7, it becomes alkaline. And so there's a fad now to buy water that is alkaline, and you can see all sorts of like, you know, laundry list type posts which show all the supposed benefits from drinking alkaline water. One experiment we do in first year chemistry, which is actually an interesting one, is an acid-base titration where you follow the pH of a solution from adding strong acid. And what you'll notice is if you add like 1 drop of a strong acid to an alkaline water that's 8.8, that 1 drop will immediately drop its pH to like 3 or something. Your stomach is full of strong acid. When you take alkaline water and you drink it, the second it touches your stomach, it's not alkaline water anymore. It's acidic water. So this little tiny bit of alkaline material that's in there, Himalayan minerals apparently, does absolutely nothing. Okay? There's no health benefit from drinking alkaline water. It doesn't stay alkaline the second it enters your system. Yes? Yeah, so online people probably missed that point, but the point was made that somebody here knew somebody who had a machine in their kitchen that would take, I guess, tap water to start with and produce water at different pHs, and had like a book of what pH water you should use for if you cut your toe or you'd use different pHs of water. I guess what I'd say about that is you'd never see one of those in a hospital, and except for maybe very rare conditions, I can't think of a reason why you would ever want anything other than neutral water for any sort of medical. I'm not a medical, or not. I'm a doctor, but I'm not a medical doctor. I'm not, as my daughter says, I'm not the kind of doctor that helps people. So, you know, there may be things I'm not aware of there. But I'd say generally speaking, there's no use to have one of those in your home. Gwyneth Paltrow, actually, we picked on her earlier in the course. She advocates for drinking alkaline water every morning with a squeeze of lemon in it. And the ironic thing there is lemons are pretty acidic, and if you squeeze lemon into alkaline water, it's not alkaline anymore, even before you drink it. It's acidic water. But this sells. People want, you know, this is what I always keep saying, is if you are trying to sell something for health reasons, and you go out there with the same message of like, oh, you should exercise more, you should eat more vegetables and fruit, drink more water, get more sleep, you know, all the things everybody already knows, nobody's going to listen to you because you're just part of the noise, if you know what I mean. If you want to make sales in that area, you have to have some new hook, either something new for people to be afraid of that you have the solution for, or some new kind of gimmick that nobody's ever heard of before, like alkaline water, or whatever it happens to be. Okay. The interesting thing is actually is the claim that if your body gets acidic, it causes diseases to thrive. And this actually comes from it's a twist of a real biological fact, is that tissues that have cancer are often found to be more acidic by a slight amount than tissues that are not. It's related to the fast rate of metabolism and the production of things like lactic acid and normal biochemical processes. It's not that the acid conditions cause the disease, it's a consequence of the cancerous tissue. So that was sort of twisted to say, oh, if your body is acidic, you're going to get diseases like cancer, therefore you should drink alkaline water. Of course, they'll sell you the alkaline water or the machine to make it or whatever. If you strongly believe that alkaline water is good for you, I'll give you the cheapest possible method to make alkaline water, which is take a glass of water, pull out your container of sodium bicarbonate, which is baking soda, and just put like a sprinkle, just like a pinch in the water, let it dissolve, and now you have alkaline water. About $5 of baking soda will probably last you your whole life for all the water you could imagine drinking. So don't, even if you just like the taste of it for whatever reason, don't buy some fancy equipment or whatever. You could do it super, super cheaply yourself, doing it that way. So alkaline water, this is that pH curve I was telling you about. Like pH 7 is neutral, pH 8.8 is what the bottle was advertising. Your stomach is around here somewhere. That means if you took 25 mils of 8.8 water and added 1 drop, it'll immediately shoot down in pH to very low numbers. The pH around 7 of water is super sensitive to any tiny amount of acid or base. So yeah, put it in your stomach, it immediately turns into acid water, which is fine. Another one which is actually, like the other one, it's not harmful, but it's unnecessary. It's a way to take your money. Or I guess it could be argued it's indirectly harmful if they're selling this as an alternative to real medical intervention. But raw water is another one. The raw water trend is actually just drinking water that hasn't been treated in any way. So you go to a river or a lake or a stream or whatever, and you just scoop water up and drink it. And it's raw. I mean raw in the sense that it hasn't been treated in any way. Because you will find people that will tell you that the treatment we do to water is more dangerous than what was in the water to begin with, which is not true, right? Look at countries that don't have adequate sanitation and look at their rates of diseases associated with that. But with raw water, what you basically do is they sell these kind of like fancy glass containers. You fill it with water, and there's a bit of like a ritualistic element to this too. Like, remember we talked about alchemy and how kind of the idea of magical, crystal energy and all this kind of stuff can be a bit related to this. So this was an ad for one such company, and it said, I carry water, this is on Instagram, I carry water with me in a glass everywhere I go. You may think it's obsessive, but it's a big part of my self-care. I'm super sensitive to the water I drink and what I put into my body. I only drink the Big Sur spring water from the land where I live. I've been drinking it for 10 years, it's part of who I am. For the last month, I've been drinking my water from this incredibly magical orb from live spring water. It's revolutionized my water experience, and I could not be more grateful. Big thanks. So that's what this thing is. There's something about that pattern. I think it's on the same thing here. And it's probably like a trademark of the company that produces it. But the idea is if you drink the raw water, you should also buy a certain special type of glass container. And this magical idea, and that's only a little bit tongue-in-cheek there. All right, let's bring up a couple of questions. We still have a few to finish off for this water unit. I've been getting a few emails of people who have missed certain units. They just forgot to do them or whatever. I'm actually working on a solution for you folks. I'm not going to just take the old one and reopen them, but I do have maybe a plan B to allow people to make up one if they missed one for whatever reason. Cool? But yeah, I know I haven't done that yet, and I will before the end of the semester. But if you miss one, I don't need to hear from you because this will apply to you whether or not you email me. Same plan. Okay. Bisphenol A is a compound that has potential to leach into drinking water from what type of plastic? And the answer is polycarbonate. 13. What recent drinking water fad focuses on drinking water that has not been subjected to any artificial purification methods? And that is the raw water from these magical orbs. The end of water. All right. This, by the way, was a sign. This was put up. There was a municipality who had a fountain, and it was kind of a big fountain in the middle of the city, and people kept jumping in the water and swimming around in there. And they were trying to discourage people from doing that, mainly because the water wasn't necessarily clean, and it was recycled and used again and again, and they were worried about people's health. Probably also they may have been worried about people's, or their own personal liability. So they put up signs like this, which were like no swimming, and like nobody did anything. Nobody obeyed the signs at all. It didn't affect it at all. So they put up the sign on the left, which says danger contains high levels of hydrogen, keep out. Realizing that water is 2 parts hydrogen to 1 part oxygen. And that worked like a charm. Like all of a sudden, nobody went in the water anymore. Just because the idea, it sounds bad, it scared people, and that solved it. So anyway, funny, interesting story. Devin says, have you ever heard of the black water, the $3 bottle of water that is just black-brown? Anyone heard of that here? I've not heard of it. I have no idea. Is it like black, or does it settle and you got to shake it up? Just black? I don't know. I've never heard of that. I don't know what it is, Devin. The only thing I can think maybe is they put charcoal in it and don't filter it out, so you're drinking charcoal with it. If it was finely divided like dust, it could make black water like that. That would be pretty harmless to you, and it would ensure, I guess, that the water, I don't know. I'll have to look into that. Yeah, I don't know. All right, so what we are going to do now is switch to our next unit, which was being a pain in the butt earlier, but it seems to be working fine now. And we're going to be working on the next unit, which is on cannabis. This one's going to be quite a bit shorter, I'd say, than the previous one. The previous one took like 3 classes to finish. This one, we could even just do it today. And this was a popular request that people have had in the past. Wanted to learn a little bit more about this subject from the side of chemistry. First time I started teaching this was when it first became legalized, which is what, like 4 years ago now? Something like that. All right, so let's jump in. First of all, I want to talk about the biology of it a little bit. In our bodies, we have cannabinoid receptors of 2 types. We call them CB1 and CB2. And the CB1 are found in neural tissue, like neurons in the brain. The other ones are found distributed all kind of over our body, and are generally, the CB2 receptors are generally associated with immune type functions. So they're associated with immune cells. They're also associated with inflammation and things like that. So the idea is we have all these receptors, and you see them on nerve endings. They're associated with pain as well. And if you take in a substance which fits in the receptor, and we call these compounds cannabinoids, then they fit in the receptor and they elicit some sort of biological response. This is sort of a general way that most chemicals behave on our body. Okay? So we do have these specific receptors, CB1 and CB2, that have only sort of relatively recently been understood to know what they were, and how they function, and how they contribute to the running of our body. And so these are present, and we also have a series of molecules that naturally occur in our body called endocannabinoids. So cannabinoids are just any molecule that fits those 2 receptors. Endocannabinoids are ones that are endogenous to our body, so ones that are like naturally present in our bodies. And anandamide, the one you see here, is the most important one, and these are used to regulate or help regulate certain functions like appetite, inflammation, pain, lots of other things as well in our body. All right, so there's natural ones, and then there's unnatural ones. And natural ones are ones that come from outside sources. They could be from things we ingest, things we inhale, things we inject, etc. But they're just any substances that can act on those same cannabinoid receptors. And this is what's going on in cannabis. And the molecule of greatest importance in cannabis is one called THC, which has the structure you see there. It has an OH, meaning it can hydrogen bond, meaning it has some solubility in water. It's not very soluble in water because it only has one OH and a lot of carbons, but it's a tiny bit soluble in water, which is really all you necessarily need. It is the main psychotropic chemical that you find in in cannabis, and it makes up about 1 or 2% of the dry weight of the dried material, dried plant. And the other one, which is much more abundant in the plant and actually a much more important component of the plant, is this other one, which is called THCA, which is tetrahydrocannabinolic acid, which looks the same except on this position it has this extra group. And that extra group actually makes it more water soluble because it has another OH, so it can hydrogen bond twice. And this can make up to 25% of the weight of a dried cannabis plant. So these two together are considered in a figure that we're going to call total THC of a plant. Mostly it's THCA, a tiny bit of it is just regular THC. So sometimes cannabis is called the devil's lettuce. To me, lettuce is not something you dry and smoke, but lettuce is something that you eat. THC, because it's present in such small amounts in the cannabis plant, means you probably can't get high really easily from just eating the cannabis plant. Because most of that total THC is in a form which is THCA, which has no psychoactive effects on the body. So eating cannabis really has probably no effect on people. So yeah, it's not really lettuce in that sense. However, when you take cannabis and you heat it up, what that does is it converts the THCA into THC, and then it becomes active. So when there's certain edibles that you can buy, and it'll list the lab analysis of the different cannabinoids that could be present in there. So you see in the back, it has it tells you that's 1% THC, it's 23.2% THCA, and then it gives you this number, which is total THC, which combines THC and THCA. And the formula is here. You take the percentage of the dry material that's THCA and multiply by 0.877, and add to that the percent that's THC, and that gives you this total THC number, which is often reported on products where they're sold. So what's going on here? Why is there two chemicals, and why does this one only count 87.7%? So we're going to look at what goes on in this situation. First of all, by the way, the concentration of both of these things in the plant are highly dependent on the stage of growing of the plant, the stage of growth. This was just one experiment that was done in 2012 where they checked the total THC content, including THC and THCA, over several weeks, and noticed very, very low, it goes through a flowering stage in weeks 5 and 6. And then all of a sudden, after like week 7, it starts to shoot up. And it hits a max around week 11. Okay, so the age of the plant when it's harvested actually controls, to a certain extent, the amount of THC and THCA you'll find in the plant. So what happens if you heat THCA, which is this one here? It does a reaction, a chemical reaction called decarboxylation, where it loses a molecule of CO2 and it converts THCA into regular old THC. So the THC is the same thing as THCA, the same molecule after the thing has been heated. So that's why people would smoke it and not eat it, because if you eat it, there's no heat, it doesn't get transferred to THC, and you don't get that effect. But if you smoke it, you do, because it's the heat that converts it and it puts THC into the gas that you're breathing. So where does that 87.7% come in? Well, it works out, if you look at how much this molecule weighs, for each mole, remember we talked about moles earlier on in the course? If you have a mole of THCA, it weighs 358.5 grams. If you then heat it, it breaks up into carbon dioxide, which is 44 grams, and 314.5 grams of THC. So if you add up those masses on the right, they will equal the mass on the left. That, remember when we talked about Lavoisier's law of conservation of mass? This obeys the law of conservation of mass, which every chemical reaction does, so that's good. It turns out if you look at the mass of the THC you get 314.5 grams of THC from every 358.5 grams of THCA, and that ratio is 0.877. So basically what we're doing is we're saying we're taking the THCA, 87.7% of that mass becomes THC, so we multiply by 0.877, and then we add to that the amount that was THC to begin with, and that gives you the total potential THC after it's been heated. All right, so we have a new unit on here. We have some questions. The first question is, what are endocannabinoids? They are small molecules naturally produced in the body that activate CB1 and CB2. What two compounds make up total THC? And that's THC and THCA, the A standing for acid. Okay. Cool. Where does the majority of THC in marijuana smoke come from? It comes from the THC after it's been heated and converted to THC from THCA. Great. Now, in terms of inhaling it, there's lots of different ways that people have figured out they could potentially consume it. A very common way is to roll it and just light the end and just smoke it like you would smoke a cigarette. Another way that people do is to use vaporizers. They could vape it. And there's a number of ways you can vape it, but I'm going to talk about one or two in particular. If you light it like a cigarette, you are burning all of the leaf material in there, and you actually are producing a lot of different compounds. You're producing soot. You're producing PM 2.5. Remember we talked about PM 2.5? And all that goes into your lungs, and it can cause all sorts of damage. There's tar, there's whatever, carcinogens. More or less, all the same stuff that you inhale when you inhale a cigarette smoke, you're getting the same stuff from cannabis. It's heated to a very high temperature. The THCA is converted to THC, and there's a lot of other chemical changes that take place inside the cigarette. Vaporizers are some sort of device which heats it up high enough to convert the THC to THCA, but not high enough to combust it. It's not like there's no fire or flame. And these are temperatures usually between 180 degrees Celsius and 220 degrees Celsius. That's what people typically use. And that gets you your THC on the other side. So you can actually buy, like, you know, for vape pens, you can buy the THC already pre-produced and dissolved in there. But another common thing is you can buy these little vape pens, and you can put dried cannabis material in them and heat them. And what it does is it'll heat it to some temperature, typically between 180 and 220. And instead of burning it, you are inhaling the THC in a different way. So your question might be, which is better? Which is the best way to do this? And I'm here to tell you which is the best way to do this. From the lens of science, not from like some personal journey or anything like that, okay? I don't know if you've ever seen one of these before. I've never seen one in the wild, but there's a machine called a volcano that you can get, which is a vaporizer, which has this sort of big bag attached. And what you do is you put the cannabis in there, turn the thing on, and you screw the like bag on, and it'll create the vapor, and it'll fill the bag, and then you breathe in directly from the bag. Has anyone ever seen this before? No. It looks a little cumbersome or whatever, but like the reason it's great though is because all of the vapor gets trapped and can be easily studied. So people who do studies on vaporizing marijuana love to use these devices because it's easy to control that you're not getting losses and things like that. It's easy to control the temperature and so on. So this is what people have found out, that if you use one of these under optimal conditions, so if you have the optimal temperature, about 54% of the THC, the potential THC, ends up in the vapor. And when you inhale it and then breathe it out again, with optimal breathing technique, your body's able to extract about 2/3 of that. So what you end up getting is like 1/2 times 2/3, which is about, what, 2/6 or about 1/3. So best case scenario, you can actually get 2/3 of the THC absorbed into your body. So this paper was published 2009, and what they did is they used this volcano device at 3 different settings of temperature, 170, 200, and 230, and compared it against the equivalent amount of cannabis rolled and smoked like a cigarette. And there's what they found. The THC amounts, the THCAs are all small because it's heated effectively in all 3 cases, so almost all of it gets converted. But the THC at 170 is really low, 4.43. Not very effective to, I guess, cause the THC to evaporate and enter the vapor phase. 200 was better, 19.79, and 230 gave the highest amount at 67.10. Compared to directly producing the smoke from burning it, you actually get about 50% more THC out of the same amount of material when you use the vape at 230. The key here, though, is in this graph, this last piece, which is byproducts. Byproducts was everything else. That was the tar, the smoke, the soot, all the garbage that goes along with the THC that people are using this for. And what you can see is that that's this 3rd column here. That's largest by far when you're smoking it directly. If you vape it at the highest setting, you can see the amount of garbage that comes out is like what? More than 3 times smaller. So you get way less of the bad stuff, right? The junk. And the actual THC, which is this one, you can see is higher here than it is by smoking it directly. So science says a vape setup, whether it's this volcano thing or a pen, at 230 degrees Celsius is the best bang for the buck to maximize THC and minimize harmful byproducts. Now that doesn't mean harmful byproducts are 0. There's still some in there. And if you lower the temperature, I guess you get a little bit less. Yes?
I've always heard that like vapes, like weed pens, are bad for your lungs.
Right, and they are. So yeah, the question was, I've heard that vaping is going to be bad for your lungs, and like smoking is bad for your lungs too. So from this report, I would say, like, to answer your question the best way. So to answer your question, which is most harmful for your lungs over the long term, you'd need to do epidemiological studies, and I'm afraid there's not a lot of that available yet. I have a good friend who's a respirologist who used to work in Nova Scotia, now he works in PEI, and what he's seen over his career, he said, is that people who are chronic cigarette smokers show, certain types of lung damage that's very characteristic, and, it takes decades, and you get things like lung cancer, you can get COPD, and he said usually you see it like low down in the lungs. What he sees is people who smoke chronically marijuana, they get different types of lung disease. It's like not the same as what you get from smoking cigarettes. Now, I don't know if he's discriminating between how, the exact methods they're using. So don't get me wrong, all of these are bad for your lungs as a long-term solution, right? If you're looking at, you're gonna do it no matter what, and you're looking at like, I guess risk reduction, there may be some ways that are gonna be safer than others. This, by the way, is just one study too, and this is pretty preliminary. And it could very easily have something new come out saying, oh no, there's something else really bad about vaping that wasn't taken into account in the previous study. But these are sort of slow to come out. And the reason is that, countries like the US, where a lot of this research is typically done, it's a banned substance still. So people just won't work with it. And it's only been legal in Canada for a few years. So these sorts of studies are gonna be slow to come out. It's been legalized in other countries, though, for a lot longer. And you do see, and we're going to look at a few, large cohort studies of people who use over a long period of time. I want to talk about the pharmacokinetics, because there's some interesting chemistry here, too. Once you inhale THC, actually your liver handles it extremely rapidly. This is pharmacokinetics of inhaling by smoking a joint. And what it's doing is looking in time. So the time span between here and here is 1 hour. And what they did is they took an 11-minute period of time, and I don't know how many, this is like 6 different subjects. And they had this thing where they have to inhale for 2 seconds, hold it for 10 seconds, and breathe out, and repeat that process once a minute for 11 minutes, I think it is. And what you see, you can see this sort of beginning part here. This is the smoking phase. Maybe it was 12 minutes, I don't know. What you see is like a rise in blood concentrations of THC, which makes sense. Once people stop smoking, of course, then the number only can go down from that point on because you're no longer absorbing it. And what you see is the THC is gone basically inside of an hour. It has a half-life, what would you say? I don't know, 20 minutes or something like that. So it's very, very, very rapidly removed from the bloodstream. And you might look at that and say, well, how come people stay high for so long if it's gone in an hour? It's because it's converted in the body to something else that is also psychotropic. What it's converted to by an enzyme in your liver called cytochrome P450 is this molecule called 11-OH-THC. We're on, this is carbon 11, they add an OH group. Your liver does that. That's one of your main functions of your liver, by the way, is to make toxins or unrecognized substances in your bloodstream more water soluble. Because if they're very water soluble, your kidneys can filter them out and you can excrete them. So it's sort of like a tag team partnership between your liver and your kidneys to detoxify things by making them water soluble and therefore making them easy for your kidneys to sweep. So it tries to do that with THC. It puts that OH group on there, and we know that adding an OH to something makes it more water soluble. It's not done there, though. It'll actually do it again over a slower time period and convert that OH to that group, which has an extra oxygen, which actually makes it even more water soluble. And that happens over a much shorter time scale. So this was a study that was done back in 1992. And what they find is that the average of 6 people looks like this, is that for the first 0.2 hours, people are smoking and increasing their blood concentration. Once that stops, which is around here, it dramatically drops within about an hour. And you see here 11-OH-THC. Okay, during the smoking phase, it starts to rise. It rises a little bit slower, but as that THC disappears, it turns into 11-OH-THC. And you can see it decays on the order of several hours. So the actual high that people experience is mostly this 11-OH THC, which is present in the bloodstream. And slowly your body can handle it and get rid of it and so on. These pharmacokinetics are actually really important because it basically describes the length of an effect that your body can expect to experience. There might be all sorts of drugs that could get people high, but maybe the pharmacokinetics are wrong and it disappears in like 3 minutes. And that's maybe not worth it for people, I guess. I don't know. The 11-OH does decay though over, it's probably gone after 6 or 7 hours. And it turns into this other one, which is the THC-COOH. And it can last, it's detectable actually for days. So if you work for a company in the US that does drug testing, or you compete in an Olympic event or something like that, and you get blood tests done, and they do test for cannabis use. I think there's a Canadian snowboarder that lost his gold medal a while back because he tested positive. This is the one they're looking for because THC is gone in an hour. You're not going to find that the next morning in someone's blood. But you can find these byproducts that actually take, many days to completely disappear from the body, or maybe even weeks if you can measure traces of it. Now this is the pharmacokinetics actually of a different material. This is if you use edibles. So it's still THC, but you're not inhaling it. Instead, you are ingesting it. And the pharmacokinetics of this are actually quite different. One that you see, this one's the THC right here. It rises and falls over like 5 to 10 hours. So that's because your stomach just takes a lot longer to absorb it into your bloodstream. It's a lot slower of a process than directly putting it in your lungs by smoking it. Now the advantage of this, of course, is that you don't do any damage to your lungs at all if you use edibles. Problem is, if you have a job you have to go to or something like that, you're probably going to be useless for a lot longer in this situation. And it does the usual thing. It converts, first of all, to 11-OH THC, and then to the circles, which is the THC-OOH. It's this first part that's sort of spread out, which makes most of the difference. All right. So I guess, based on this study, they're saying it takes like 24 hours for it to leave your system. This last one, I think, is not psychotropic. It doesn't have any effect on your mood or anything like that, but it does hang around a long time. When I say that it's not psychotropic, it's probably not a cannabinoid in the sense that it does not interact with your CB1 or CB2. By the way, those CB1, CB2 receptors, where they're placed actually is responsible for a lot of what people perceive as sort of side effects of cannabis use. One of them being hunger. Appetite is directly influenced by the presence of these CB1 and I think mostly CB1 receptors in that case. So often people get the munchies, right? And that's related to the specific parts of the brain that are targeted by these chemicals. And that actually can be a good thing as a form of treatment for people who maybe have low appetite for whatever reason and they need to be eating more. Not a problem I have. Which cannabis consumption method delivers the highest amount of THC? Smoking, high temp vaping, low temp vaping. I don't really like this question. I don't know what I was thinking when I made it. Because I guess eating, if you consume edibles, you're getting all of it, right? I don't know what I was thinking when I made this question. It's going to be either B or C. It's definitely not A or D. Probably eating, I guess. Does it tell you if you're right if you guess it? I can go into the chat question and see what I was thinking when I put it there. What does THC first metabolize to once it's in our bloodstream? This one, 11-OH THC. What THC metabolite remains in your system for several days? That's D, THC-COOH. So this whole biochemical series of products that it makes before eventually your body can get rid of it. So edibles, are another interesting thing, and edibles are obviously things you can buy, or they're things that people make as well. THC itself is more or less non-polar. It's got an OH, which makes it a little bit polar, makes it a little bit water soluble, but it's hard to dissolve very much of this in water. It's hydrophobic. It's another way to say it. It prefers to be in like, it dissolves well in like oily or fatty materials, but not very well in water. So to get THC then extracted from the plant, you need to find something, first of all, that'll dissolve in, and second of all, you need to heat it to get rid of the COOH, to make the THC out of the THCA. And so butter is actually a perfect solution for both of these things. What a lot of people will do is take the cannabis, heat it in hot butter for hours. That'll extract the THC out of the plant material, and it'll also be hot enough, you can heat it hot enough to convert the THC-A to the THC. So butter's good, and it has to do with the hydrophobic nature of the THC molecule. So you take butter, take cannabis powdered, you boil it, you heat it up, simmer it for like 3 or 4 hours, and then you want to filter off the kind of gross plant material. And you can see by the color here that there's a lot in there that's not just THC. THC itself is white solid. So it actually extracts a lot of other crud out of the plant too. And you end up with like this butter. And then you can use that butter to make brownies or whatever else, and you have your pop brownies or cookies or whatever you like. This is done industrially using a different method. They don't use butter. They use a process called supercritical carbon dioxide extraction. So you can buy these machines, and what a supercritical fluid is if you take a liquid, like water, and you heat it, it'll boil and become a gas. If you then pressurize the gas at a certain regime of pressure and temperature, you get something called a supercritical fluid, which is like a gas, except you'll have like small numbers of molecules of water or CO2 clustered together. So it's like kind of in this range over here. We call them supercritical fluids. They're high temperature and high pressure, and you can exist in this regime. And so supercritical fluid has the advantages of gases in that they can penetrate anything very easily, they move very fast, but they have the advantages of liquids in that they can dissolve things. So these machines are used to industrially extract nonpolar substances from plant material. They can be used for getting THC, for first of all decarboxylating it and then extracting the THC. It's also used a lot to decaffeinate coffee beans, remove the caffeine from the beans themselves. So this is what's called a phase diagram, and it shows you what phase of a substance will exist under what conditions of temperature and pressure. So for carbon dioxide, if you heat it above 300 degrees Kelvin, which is just a little bit above room temperature, and so hotter than this temperature here, and under pressures higher than 100 bar. So 1 bar is like atmospheric pressure. So it's like 100 times that. So very, very high pressure and high-ish temperatures, you get this supercritical fluid, and that will extract the THC out. And then they can add the THC to, gummy candies or whatever it is. There's a movement now to try to produce THC-infused beverages. And the idea here is, you can claim that THC is bad or whatever, but it's hard to make the argument that alcohol is fine and THC is bad. Like, either you concede both of them are bad things, or you kind of agree, well, maybe both of them are okay. They may have different effects, and they may have slightly more impact on some than others or whatever. It's not that simple as good or bad. But nevertheless, there is believed to be a market for beverages that contain THC, just because when people are out at parties or bars or whatever, drinking a beverage in your hand is sort of the social norm. The problem, though, is that the THC is really hydrophobic and doesn't dissolve in water. So how are you going to get it to dissolve into a drink that you could then have in a can or whatever? The solubility of THC in water is 2.8 milligrams per liter. So that's not very much, considering like an edible is like 10 milligrams. And so to get that much from a drink, you'd need to drink like 4 liters of something, which is, you know, kind of a lot of liquid. So what are some solutions? Chemists are full of solutions, right? One is using this material called brominated vegetable oil, which brominated vegetable oil can help oily material emulsify in water. This is basically just taking regular vegetable oil and you treat it with a chemical called bromine, and it makes these molecules that have a bunch of bromines on these long chains. Bromines are very heavy elements. It makes this material very dense. And so by mixing it with natural oils, you can actually exactly match the density of water, and then it doesn't sort of float to the top anymore. You can have it disperse in water. They're commonly used in beverages that are like citrus-based, like Mountain Dew uses it, Gatorade at least used to use it, and it helps like the citrus oils stay distributed in the water, like an emulsion. We talked about emulsions before. In the water unit, we talked about how flocculation breaks emulsions. Maybe we didn't talk about emulsions. Emulsions are more like liquid in liquid. But anyway, what this BVO, or brominated vegetable oil, will do is allow oily materials not to dissolve in water, but at least remain suspended in water without floating to the top. So Mountain Dew, brominated vegetable oil is one of the ingredients you see there. Another method, and there's a lot of active research actually going into this, including some research here at Acadia, there's these molecules that are called cyclodextrins. And they're these kind of like cup-shaped. They're kind of shaped like a Reese peanut butter cup, like the little ones that come in Halloween. And what it looks like, it's this ring of sugar units. And your body can actually break this down and use it as like fuel, sugar. But what it does is it creates this sort of bucket-shaped molecule where it's hydrophobic on the inside and hydrophilic on the outside. So the whole shell, you know, it kind of is moving through water. It dissolves quite well. But the inside has this hydrophobic place, which is a perfect place to put a molecule of THC. So like little buckets, each bucket carries around a THC and keeps it dissolved in water. There's different size buckets depending on the molecules that you want to put in the bucket. You can have with 6 glucose, 7, or 8, and they change the shape and the size and so on. So you can pick the right bucket for the molecule that you're trying to make dissolve in water. And then what happens is you have your sort of guest molecule, and it goes inside. And once it's inside, it's in a hydrophobic place. And the bucket's happy too because it doesn't want water in there if it's hydrophobic. So if something hydrophobic goes in there and kicks the waters out, everybody's happy. The waters don't want to be in there either. It turns out THC solubility goes from 2.8 milligrams per liter to like 14 grams a liter, up to 14 grams a liter by using these cyclodextrins. So this is another way people are trying to find ways of making these things more water soluble. You can't just start adding OHs to the molecule because then that makes something else, makes something different. It's not the same thing anymore. All right, what liquid would THC be least soluble in? Here's an interesting chemistry one. Water containing cyclodextrin, no. Pure water is pretty bad, right? Water containing BVO, no. BVO makes it more soluble. Less polar liquid, such as ethanol. So it turns out if you use less polar liquids, they dissolve nonpolar things even better. Gasoline would probably be great. Of course, you don't want to drink a bottle of gasoline. 8. What phase of matter exists at temperatures and pressures higher than the critical point? That's supercritical fluid. What are cyclodextrins? Ring-like compounds made of sugar units. Or bucket-like, maybe I should say. Our last little bit here, we have like 5 minutes left, and maybe that's enough time, is toxicity. There's a myth out there that you can't overdose on marijuana. And that myth actually comes from a paper that was published in 1984, where that paper published saying there are no known causes of THC overdose, which very well might have been true in 1984, but 1984 was a long time ago, almost 40 years ago. And there have been many THC poisonings causing death since that time. THC is a chemical like anything else. And like anything else, including water, it's going to have an LD50. It's going to have possible toxic effects, eventually at some dose. The key is knowing what that dose is. Well, it's been measured for dogs. Oral consumption is around 3 grams per kilogram, which is actually quite high. Considering edibles, the highest amount legally allowed in Canada for edibles is 10 milligrams per unit. So this is a kind of candy that has 10 milligrams of THC in each candy. And if you weighed 60 kilograms, that means you got to eat about 1,800 of these to reach the LD50 value established in dogs, which is, I don't know, not very realistic. Rats, though, the toxicity is lower. It's 1,270 milligrams per kilogram was discovered for rats. That's only about 800 of these, which they come in 10 packs, like each bag has 10 candies. So it's like eating 80 bags of these in like 15 minutes, which not super easy to do. However, there are other products that have much higher amounts. Although not legally allowed in Canada, or at least yet, they do exist. This is one that I saw for sale on the internet. They have 240 milligrams of THC per candy, and they're like shapes of like little Lego men. You have to eat 32 of these to hit your LD50. This would be easy to do, especially if you're a child and you're a lot less than 60 kilograms and you don't realize that these aren't just candies. And this is where a lot of these overdose deaths are being found in. Part of it is because there's websites selling these things that like try to copy actual packaging for real candies. So it's not hard to see why kids would be confused. They taste the same, they look the same, and you see this problem arising more and more. Smoking it, though, is actually rough, like to try to poison yourself by a direct overdose. It works out, it's about smoking about 2,000 joints at once in 15 minutes is about what you'd have to smoke and absorb all of it to hit your LD50 value that's established in rats. So I'm not saying like, smoke away with impunity. There's other problems, but overdose due to THC toxicity is probably not going to be a major worry if this is how you're consuming it. On this picture, there's 720 little joints. So you need to have 3 times that many to overdose, based on that number. Injection, though, actually the LD50 is a lot lower. So again, it's all about how it gets into your body. It can have stronger effects or weaker effects. Probably one reason, actually, why THC is not that toxic if you smoke it is because it takes a long time to smoke it, and we know your liver gets rid of it really quickly. So it's probably hard to have it build up to a really toxic point, but it would be a lot easier to hit that if you injected a large amount in one shot. So that's possibly the reason behind that. How much do I have left? Just a couple of slides, but I don't have any time left. So I think I'm gonna have to stop now. Maybe we'll spend like a minute on it next class on Thursday, and then we'll start another new unit then. Cool, so this was just a short little thing, but hopefully people found it informative